Hi, everybody. My name is John Downey. I'm Vice President and Chief Innovation Officer at Woolpert, here today to talk to you about shifting your enterprise to the geospatial cloud. Just a brief agenda. I like to do these presentations by telling stories, and so I'll tell you three different stories today. One is a customer-related story. One is our internal story and our journey to the cloud. And the last is a journey that we just started pushing off on. So it's still very new, and we'll expose you to how we're doing an internal project from the beginning to end as well. But before I get started, for those of you who may not be too familiar with Woolpert, I'll give you a little bit about Woolpert by the numbers. Woolpert traditionally within our geospatial practice has a huge investment in technology. We've been in the game for well over 50 years. That technology investment is both in sensors, compute technology, processing software, innovation and R&D projects, and in training the people to operate those systems. And as you can see, we have a significant amount of geospatial professionals within the firm, currently over 400 and growing. You can also see we've done a lot of LiDAR and imagery projects, lots of statewide projects, hundreds of counties of imagery collected, and a few more numbers at the bottom around the square miles collected, number of aircraft, and current numbers of sensors that we own. Just a little bit to give you an idea of the scale at which we're operating. Why Woolpert? And the way I would summarize this slide is just to say Woolpert has the staff and the expertise to help you get the most out of your GIS. Whether it's an implementation service, dealing with big data, producing graphical outputs or interactive web maps, we have staff that has done that and has been performing those types of services for many, many years. The first story I'd like to start off with, shifting your GIS to the public cloud. This is the story of Panama City, Florida. Start off by giving you a little bit of backstory. Panama City was an existing GIS shop. They were running ArcGIS Desktop. They had some apps and data deployed into ArcGIS Online. Not unfamiliar to a lot of folks. They had some infrastructure that was aging out. It was all in-house if it wasn't in AGOL. They had the typical lack of IT staffing and support and tight budgets. Their focus was currently on performing the day-to-day tasks to maintain and operate the GIS. This project really became a project because of a very key decision made by the city. And that was that they wanted to implement the Azteca CityWorks, or Trimble CityWorks now, asset management system. And that is an asset management system that many of you know is very tightly coupled with the ArcGIS environment. The Panama City project started off with implementing CityWorks asset management system. The challenge that popped up during this implementation had to do with a technical incompatibility between ArcGIS Online and CityWorks AMS. We needed an ArcGIS Enterprise server to integrate with CityWorks AMS. And so we looked at the city's infrastructure, performed a technology assessment, and we found pretty much what we were told we were going to find. We found the aging servers, we found lack of internal infrastructure support, and really a need to implement some modern best practices. So from this assessment, we developed a plan, and that plan was specific to solving the issues at hand. What we wanted to do was be able to provide long-term support for infrastructure as it's integrated with CityWorks AMS, and we wanted to offload that burden from the city. So Woolpert will provide the long-term operational support, so we no longer have to rely on non-GIS specialists to maintain that GIS environment. So what did this journey look like? The first thing we had to do is we had to choose a public cloud provider. Part of the plan was to migrate the city's infrastructure from the on-prem environment to a public cloud environment. We went through, assessed the typical vendors, Amazon, Microsoft, Google. We selected Google based on two main criteria. One was the overall feature set in the cloud that supported this specific use case, and the other was on pricing. At the time we did this project, Google was the best fit, and it still maintains its position as the best fit for this type of project. The interesting thing is that CityWorks AMS itself is actually running in AWS. So you would think that it would lead you down that AWS path immediately, but as mentioned previously, it was kind of the feature set we needed at the moment, and the pricing that really brought us down to this other cloud environment. The good thing is both systems function flawlessly in a hybrid cloud environment. So we're able to take advantage of very specific infrastructure and very specific pricing for this particular implementation. As part of this, ArcGIS Enterprise was deployed to Google Cloud Platform. Typical deployment, setting up a virtual server, deploying the production software into that environment. And then we finished off with two major integrations. The ArcGIS Online environment was brought into and connected to the enterprise environment, and the enterprise environment was also connected with CityWorks AMS. So this is what allows us to bring our investment in GIS into the asset management system. And when this whole journey was over for the city, what did things look like? The way it looks at Panama City today, they have a fully functioning Esri Enterprise GIS environment integrated with CityWorks Asset Management, running inside of a scalable public cloud environment. And that environment is fully managed by our Esri, CityWorks, and Google Cloud experts. So we're providing the managed service component. So it's an entire turnkey solution that is hands-off as far as the management is concerned for the city. Some of the major feature wins we got out of this, the environment is fully backed up, not just the data, but the actual configuration of the machine. So should something happen, we can redeploy this entire environment from the ground up in a matter of minutes. And we can do that from anywhere in the world at any time. There is absolutely no IT support required from the city. One caveat, though, we take any assistance that we can get. If the IT group wants to be part of it, absolutely. If they want to manage it, we are 100% for that. We can train them on how to do it. Out of the gate, we don't require anything. We can handle the whole turnkey solution ourselves. So let's think about a few other details, right? We kind of glossed over some things in the story. Just to keep it concise, I'd like to dig a little more deeper into a couple different items. There's really four things that we looked at in this project that really needed to be considered and really took the bulk of the effort. The first was that selection of a public cloud environment. We had to determine exactly what we're looking for. Were there any pre-existing IT contracts or other contracts with the city that we need to leverage that might have brought in pricing discounts? Were any other providers involved from the IT side? Was there any reason that we need to go one way or another that we didn't know about? Then we had to answer, did we have any vendor-specific issues? Was there anything that Esri would not support in GCP? I think some folks might be aware that they have templates in AWS and Azure that are easy to spin up. Was there going to be an issue on the technical side there? And what about non-Windows? If we wanted to do a non-Windows deployment of ESRI, which we did not do in this case, but if we wanted to do that, was there any technical roadblock there that one cloud vendor or one technology vendor would have put into place? And again, in this project, it was a very straightforward process. We were able to deploy directly into GCP. Who is going to be responsible for support? That's always an interesting conversation when you talk about cloud. Is Woolpert responsible to maintain the infrastructure, but a client maybe is responsible for patches? That all needs to be documented. Who is going to provide backups? What's the backup cadence? In this case, we script the entire stand-up of the infrastructure. So we look at infrastructure as if it's source code so that we can script that whole thing and redeploy the whole infrastructure and environment in a matter of minutes. We also have to determine who's going to be responsible for disaster recovery and how. What are they going to do? How are we going to secure backups? All that has to be documented. And then you get into the real nuts and bolts of cloud deployment. What kind of service level objectives are we going to define? And what service level agreements are we going to put in place that guarantee uptime and have the engineering processes behind them to be able to provide guaranteed uptime? And then also, how much redundancy, how much resiliency do we want to build into the system? If you look at a base deployment, which is exactly what we did for Panama City, it's simply what I would consider to be a very basic shift from enterprise that is on-prem to enterprise in the cloud. We replicate the current environment. There's not much in the way of duplication of services here, which keeps costs down, but it does add a little bit of risk here. We do things like daily snapshots of the VM or virtual machines. We have some logging and alerting systems in place to let us know if things are going awry. And we have the ability to stand the whole thing up, as mentioned before, very, very quickly. But what we did here is this is kind of a very plain deployment. The other option in this case is to go with a multi-server deployment. You get a lot of benefits here. You have load balanced services. You get to break apart the different services. as they need to scale differently, they can scale differently. You can use SAML or any kind of authentication here to access the environment. And you've isolated the performance of each individual component into its own little area. Very scalable when it's deployed like this, but it also has an impact on cost. It is going to be more expensive depending on how it's licensed, how many of each component you have, etc. So I think really the point here is there's a broad range at which you can break up this type of deployment to provide an appropriate level of scalability, of disaster recovery, of redundancy, etc. And that really has to be thought through early on in the project because it's going to have a big impact on how you're actually going to deploy. Final thing really to say about this type of project in general is I want to talk a little bit about how we think about getting started. This is what our typical cloud journey looks like. It's very simplistic when you break it down like this, but we'd start with the first of 5 phases where we decide, do we want to go to the cloud? Yeah, we think we might want to go to the cloud here. Okay, what types of workloads? What's the use case? What's driving this? We talk about all that. We make that kind of decision point. That all happens in kind of a pre-sales mode. It all happens up front before we really get going on the project. Once we've decided, we enter the assessment phase. We look at what is feasible, what can we do, what can we accomplish, and based on the outcomes of that assessment, we then plan the project. What are we going to do? What is the design going to look like? How are we going to deploy? What components are going to go where? Who's going to be responsible for what? Once the plan is written, we deploy it. Everything goes into production. Everything is implemented. Everything's tested. And then the last part, which really never ends, we optimize. We look at the planned deployment. What happened? Are we oversized? Are we undersized? Where can we potentially help optimize cost and deliver more performance? And it's a very iterative approach in this cycle. One last thing I'd like to say on this. Not everybody starts at the same place on this journey. Some folks start with a decision up front. Some folks have already have their plan baked and they're just looking for someone to help to deploy it. A lot of folks will come in and will actually look at it somebody else's post-deployment and will help optimize that. So again, bring in cost savings, bring in reduction of resource requirements and needs, etc. So anywhere on this journey, we can start anywhere, we can stop anywhere. But just kind of give you guys an idea, a broad overview of what the typical journey looks like from beginning to end. I'd like to shift gears a little bit, and I'd like to talk in the context of Woolpert's own journey, where we lifted one of our systems that we had in production from the on-prem environment and built it in the cloud. And that system is RASTER. RASTER is our cloud-hosted, fully cloud-native raster tile service. It easily integrates with any GIS or web mapping system through WMTS or XYZ URL templates. It's fully scalable, both in the storage side and the data ingestion side, and the ability at which we have to stream a virtually infinite number of tiles per second. It has a full disaster recovery plan that includes automated redeployment baked in as part of this. And what we simply look at it for is it relieves the pressure of needing to store gigabytes or terabytes of data, create caches, and worry about how those caches are maintained, how they're backed up, how they're streamed out to the web. That entire problem is shifted away from our clients' purview into ours. So you gain Woolpert's expertise in the management side of things to be able to manage that data, manage that system. How does it work? I won't go into too much detail here. Basically, we're taking your imagery that exists now. It could be in your data center. It could be on a disk somewhere, on a thumb drive. It could be in the cloud already. We're running that through what we call a pipeline, where we take that data and we pull it into the RASTER system. We take the source data, we create the image pyramid and the necessary metadata that we'll use to serve that back to you. The source data is maintained in very highly durable cloud storage. The tiles are maintained in that same type of very durable cloud storage as well. So we're using very commodity data storage to service RASTER. Once we have the data ingested into RASTER, it is as simple as a user provides authentication and they can stream that into a myriad of different systems. We can look at web map, anything from the ArcGIS JavaScript API, Google Map, Mapbox, Open Layers, It could be pulled into mobile platforms as well. The iOS Maps SDK, for instance, you can use it in a number of desktop GIS systems. And it can be cataloged through any type of data catalog or metadata system that you have out there as well, because it has that full metadata exposed with it. So really, once it's in StreamRaster, anything that can do WMTS or XYZ tile requests can consume this data directly from the cloud. So just giving you a couple screenshots. This is downtown Columbus area in the ArcGIS API for JavaScript, and it is pretty much exactly what you would expect. It is the imagery seamlessly streamed into a web browser. And here's a different county in Ohio where we're looking at that exact same data streamed into ArcGIS Desktop in this instance. And as you can see from the catalog interface on the right-hand side, our StreamRaster connection doesn't just hold one data set. We've got what looks like 10 or 12 data sets that are available to be added as independent layers into the desktop environment. So you could have one or more on, use the swipe tool to swipe back and forth to compare images over time, or simply just have access to them if you need to go back and look at historical data. The nice thing here is StreamRaster can store all this data in a very organized fashion. It can create all the image pyramids that it needs to serve this data back expediently, and that all can be just kept in one nice, clean interface for a client's consumption, the public's consumption, a consultant's consumption, etc. So to us, what does StreamRaster really represent, though? It represents a cloud-first mindset. It is a serverless technology, meaning there's not virtual servers out there running, powering this. It is managed by the cloud provider. So we don't have to worry about server uptime, how many cores, how much RAM we're going to use, how much data storage. It is built on open source libraries. We made this decision because we wanted to be able to change its behavior should a use case come up that dictates change occurs. It's built in what we call a microservices environment, where we have broken up its independent components into tiny little web services. So if the component that is responsible for serving a tile from StreamRaster to a web application becomes overused, it can spin just that little component up, and then it can spin another one up as demand is needed. And another way to look at that is, if we're ingesting a bunch of data, we want to do that very quickly, and then we don't need to have any available resources that are focused on ingestion. So we can spin up a bunch of ingestion resources while we're processing that data and bringing data into the system, and then we can get rid of all those once that data is there, because we're no longer concerned with bringing data into the system. That part's over. Why that's important is because now we're not paying for those servers that ingest. All those resources are gone. We use a multi-regional redundant storage scheme in StreamRaster. What that allows us to do is we have multiple copies of the data. So should something happen in one cloud region, StreamRaster can take over in another cloud region and start serving tiles directly from there. So we're not dependent on one specific data center being online 24/7, 365 to be able to serve this data. And finally, there's a whole API management and security layer that is given to us by our cloud provider that allows us to manage and secure this cloud environment on a customer by customer basis. Just to give you a sneak peek, this is Google Cloud Platform's Cloud Console, and we have a specific StreamRaster project loaded up in here. The big things to see is, if you look kind of at the bottom, this is a private API. So we enable it on a client's project, and then they have access to it. Once they have access to it, we'll help them load their data, get it published, secure it by creating credentials and delivering those credentials to the developers who need those to be able to access the data via desktop or pull it into a web map, mobile app, anything like that. We also have the ability here to see how many requests come in. So we're looking here between a 9 a.m. and 2 p.m. time window. We can see there were about 6,500 requests for images from StreamRaster. So we can start to look at how those requests trend over time and how was latency during those requests. So if you can see here, our median latency is 131 milliseconds. So essentially 1/10 of a second to get an image from the time we get a request to the time you have the image back. And up to the 95th percentile, we can get it back in 0.3 of a second. So very fast all the time. And we can manage it and see all that data through the management console as well. So it gives us a lot of tooling that we did not have to build ourselves to be able to authenticate usage, et cetera. That is all given to us by our cloud provider. So it makes, again, something we don't have to worry about maintaining. We don't have to worry about upgrading or adding new features as time goes on. All right, so having walked through the last two stories, I'm going to shift gears again a little bit. I'm going to talk to you about what we see happening with deep learning, how that is impacted by the cloud, and why we see this as part of a larger shift of an enterprise into the cloud. First, I want to talk about deep learning. You've probably heard a bunch of different names around this: artificial intelligence, machine learning, deep learning. You may have heard about neural networks in different types of readings or articles. But what it really is to us is data structures and the algorithms to help a machine be able to help us extract data from our data. So let's look at kind of a compare-contrast analogy here. The first example I have with machine learning, this is what a typical machine learning project boils down to. We have some data input. We have some form of a data technician extract a bunch of features that we want to find. So in this case, we have aerial imagery. We want to find all the cars in the imagery. So somebody will go in and they'll clip out 100 or 200 cars. And we'll throw those cars into a classification engine. And that classification engine is meant to learn what a car looks like and then classify in all the imagery, all the objects that it believes is a car. And so what we essentially get is a set of what are cars and what are not cars as an output. The key point here is we have a human in the loop. We have somebody responsible for creating the data that we're going to use to train the system. But what we really want to do is we really want a system that we don't have to be as in the loop on, where we start with the same input, but the feature extraction and the classification is actually happening in an algorithmic way. The computer is able to determine from a very few sample images what is and is not a car. It's able to continue to refine what is and is not a car over time, create a better, more robust set of information that helps us classify cars of all sizes, all types, in different parts of a city, a county, maybe a state, or maybe different parts of the world. So we want the computer to be able to reason and to understand what that looks like so that we can get the same output, car or not car, but we do it without the human in the loop. That's a very expensive piece that we're able to remove out of the system when we shift from a typical ML journey to a deep learning journey. So let's talk for a second. What did our deep learning journey look like? It all really started in 1969 with our photogrammetry practice when we started collecting imagery. And the rubber really hit the road somewhere around 2010, 2012. We started looking at the need to have a very robust solution to extract features from the imagery that we collected. The idea here is I want to be able to classify buildings, roads, impervious surfaces, tree canopies, sidewalks, those kinds of objects from inside of the data that we were collecting, right? There's really two ways of accomplishing that. We can build a team and we can throw hours and people at it to go out and manually extract it, or we can start to look to use software to extract that out. Moving forward, it was in about 2019 that one of our research scientists started coming up with a way to apply deep learning to move us from the machine learning environment to a true deep learning environment. And that is what we're out in production with today, as we've got the ability to create models, train models, et cetera, to find a whole bunch of different features through this deep learning process. And so now that is coming out as a offering, and it's being done at cloud scale. So I'll talk about the benefits of deep learning. It's being able to offer a product in record time with amazing quality at the lowest cost possible. And we can't do that with humans in the loop. We have to do that with a machine-only approach. And we can't necessarily do that with on-prem infrastructure because we just don't have enough of it. In some cases, it's not new enough. In some cases, that infrastructure is already being used to do other things. So it's really these three things that drive us forward. And what it does is it brings us into this mode of operation where we need to get outside of the walls of our office and get up into the cloud to be able to balance these three against each other. We want to be able to get that product created quickly. We want to be able to train on it even more than we can do now, so it's of the highest quality. And we want to be able to do it at the minimum cost again. So we've got the ability to get outside the infrastructure and do it there. But what we're really doing is we're generating or creating a very repeatable self-improving system. So we're able to do the same thing over and over and over again. And every time we do it, it's getting better at doing its job. So talking about the kinds of data that we get out of these types of systems right now, everything in the blue box is capability that is out there in production ready today. So you can see things like 2.5D buildings, flow lines, we can see crowns. And then there's a whole laundry list of things we have on the side that we're currently working on or have completed between the time that we put the slide deck together and now. So to put that into a picture, because I think it just speaks for itself, we're going to show you some examples that we did in Columbus, Ohio, where we took a publicly available national scale data set that's available from Bing, and that's this kind of light blue on the left. And we're comparing it with the same set of buildings that we created with our process. And what you can immediately see in the middle is you see a lot more detail at the building by building level. And then when you lay them on top of each other, as we did in the right-hand pane, you really see the difference. You can see that there's overgeneralization in one data set. There's even a little bit of a positional shift in that data set. And you can see what a high fidelity output versus a low fidelity output looks like. So kind of knowing where we got to, we want to talk about what a typical deep learning journey looks like. We look at this as a very agile type project. Yes, we have 10 steps here. Yes, we follow these. But depending on the type of inputs we have and the type of outputs we have, every project is a little bit different. Because everything's different, we're going to start off with data discovery. And that's really defining the use case. What are we trying to do? And what data is available to solve this problem? Once we know what data is available, we want to move on to what we call a feasibility study. What can we actually do with that data? Some data have licensing that is restrictive and we can't create third-party products off of it, or a derivative work as it's known in most licensing schemes. And some data is just not of high enough quality, not enough resolution, not enough spatial accuracy to support the use case that we've defined. So we have to go through this data exploration, as you can see, in more than one phase of the project. Once we've determined that we have the right data, then we have to select the best algorithm to get the result out we want. And if one is not on the shelf, we have to go decide what it's going to take to create that algorithm and then go out and actually create it. Once we understand where the data is coming from, once we know what kind of algorithm we have, we want to create what we call a minimum viable model. We're going to take the data, take the algorithm, we're going to run it through the process and evaluate the outcome and then present the results. And we're going to do this multiple times to where we are convinced and have proven that the results that we're getting meet what we defined in the use case or meet the business demand for the data. Once we've met that demand and we've done that in a proven and reliable way, we're going to plan the deployment. We want to make sure we get it right the first time. Then we're going to operationalize it. So we're going to shift it into production. And then what you can't see under 10 is the actual, we're going to do it. We're going to go ahead and create the data and deliver that and complete the circle here. So why do we consider deep learning part of the geospatial cloud? And why do we get so excited about it when we talk about it? It's not until you truly embrace the concept of moving your geospatial environment to a cloud environment that you can start to unlock a lot of the inherent value that is buried in your geospatial data. How many features are you missing that you don't know about in your GIS now that you could find through a process like this? That's what we really see shifting to the geospatial cloud opening up for us. There are things that we can't do on-prem with your data that we can do at a cloud scale. It's either too complex, too computationally intensive, takes too long, is too expensive to do it in an on-prem environment. So we move that data out to the cloud, move the systems out to the cloud. Now we have the ability to leverage all that data and leverage those systems in ways that just aren't possible in most on-prem environments. I'd like to thank everybody for attending today. At this point, if you have any questions, you can feel free to follow up with me. john.downey@woolpert.com is the best email address to get a hold of me at. Don't hold back. I love the question and answer side of things. Definitely email me and I'll get those answers back to you as quickly as I possibly can. And again, thank you all very much for attending.